Okay, so in this video I really want to make concrete a concept that I have been talking about and since the start of this playlist. In fact, my first video, what I did was I showed you how field automorphisms corresponded to permutations of the roots, which would such that when you permute those roots in that way, every algebraic relation that the roots satisfy in your splitting field is preserved, basically. So let me just write something down. So we've been discussing this Galois group, the Galois group of a splitting field. So it's written Galois of K over F, and this is the group of automorphisms, of field automorphisms of K, morphisms of K, which fix the ground field F, field F. So we had some polynomial f of x which did not split in the ground field F. So we extended it. It was an irreducible polynomial if you want your field extension to be a field. So we continually extended our field by taking polynomial rings with coefficients in this field and modding out by the principal ideal generated by this, and then continually doing that, splitting your polynomial down, adding roots on, and until you can until your polynomial completely splits into linear factors, and then you get your splitting field K. But what I showed you is, in the first video I showed you that each of these field automorphisms, each field automorphism corresponds to a permutation of the roots. I.e., a field automorphism will map roots onto roots of the polynomial. Corresponds to a permutation of the roots of the polynomial. And if you apply it, so if you have any algebraic equation, so for instance, let x, y, and z be the roots. So let x, y, z be the roots of f of x. Then let's say we've got an equation, x squared y is equal to some f, where f is an element in your ground field. Then if this is satisfied in your splitting field, then if I apply the field automorphism, x squared y is equal to phi of f. So phi is a field automorphism, so phi is an element of the Galois group of K over F. And if I apply that to this, then because it's a field automorphism, I can split this up into phi of x squared phi of y is equal to f, because f is an element of the ground field and all of these fix the ground field. Therefore, whatever these two roots are mapped onto, and they have to be mapped onto other roots, because when you operated it on this polynomial over here, it had to map roots onto roots. Whatever these are, it's still whatever these are mapped onto. So let's say that let's say this specific field automorphism swapped z and x and fixed y, then we'd get y squared, z squared y is equal to f, and that would have to be true too, because otherwise it wouldn't be a field automorphism. What I want to show you in this video is I want to show you the other way around. I want to show you that if, and I've said this all along, I told you this in the first video, if phi is a permutation of the roots, such that all algebraic relations, involving the roots and elements of the ground field, are fixed by the ground field, are fixed are fixed under this permutation. So for instance, if for every possible equation that these satisfy of this form, this permutation, if I just permute the roots, so for instance if I swap x to z and maintain y, if it's all satisfied, then this permutation corresponds to a field automorphism. So it works both ways. Ground field are fixed, and elements of the ground field are fixed under the permutation. I.e., they're still true after the permutation has happened. Then that permutation corresponds. That permutation corresponds to a field automorphism. I'm going to show you which field automorphism. That permutation corresponds to a field automorphism. To a field automorphism. So I'm showing you that there are two ways to look at the Galois group, basically. You can look at it as a group of field automorphisms of the splitting field which fix the ground field. You can look at it as that. Or you can look at it as a group of permutations, a subgroup of, let's say this polynomial has degree n, degree equals n, then the permutation group of the roots, you're going to have n roots, so it'll be a subgroup of Sn. So you can look at it also as being a subgroup of the symmetric group on n letters, of n elements rather, which happen, all of these permutations in this group, subgroup of this, happen to fix every possible algebraic structure that you can come up with, basically. Those are almost like the two faces of the Galois group. And this one's very, very important conceptually. That's very, very important in the fundamental theorem of Galois theory. But as far as actually finding the Galois group, this view is far more important because, okay, yes, we can't check absolutely every equation, but if we find an equation that it's not trivial that it's true that any permutation fixes it. For instance, if I had an equation like x plus y plus z is equal to f, then it's a bit trivial that the permutations of the roots fix this. In fact, all permutations S3 fix this because it's symmetric in x, y, and z. But something like this, which isn't symmetric in x, y, and z, if you find an equation like that, and you find which permutations of the roots fix this equation, then, well, firstly you can eliminate some of the permutations. If a permutation does not fix this, then that permutation goes. It's not in the Galois group, is it? But basically, what we do is we take one equation like that, we find which permutations fix, keep it true, maintain it true, and we guess that that's the Galois group. Obviously, we can't prove it for absolutely every single algebraic relation you can conceive of, but we guess, and we sort of, that's the way we actually, in practicalities, construct the Galois group, rather than trying to find all the field automorphisms of a massive great field. And when I learned Galois theory, this confused the hell out of me because I thought this was Galois correspondence, the correspondence between the two faces of the Galois group, but this is not Galois correspondence. Galois correspondence is between the subfield structure of between all the fields between K and F and this Galois group. We're coming on to that. That's far, far deeper than this correspondence here. But we need to understand this first because this is how we're going to calculate Galois groups. So when we come to the cubic and higher cases, we're going to calculate Galois groups by looking at algebraic relations and finding the permutations of the roots which fix the equation, basically. Okay, so K. So let's explain why this is true then. So K is a field extension of f, and it's got all the roots in it. So if we think about this, then K must equal the form that K must take on is it must have all the normal elements of f in, so every possible element of f is here. Then it must have every possible element of f. In fact, I'm going to do this with a specific example rather than keeping it nice and general. So I'm going to take a specific example. So the biquadratic extension. So I'm going to take the polynomial A biquadratic extension is basically just two quadratic equations multiplied together. To simplify matters, so that I don't have to use the quadratic formula, but of course we know that all quadratics can be reduced to this form, or they're equivalently this form just by a translation. X squared will have minus 2, x squared minus 3. So that is going to be the polynomial we are trying to find the splitting field of. So basically, what's in the real numbers, what does this factor into? It factors into x minus the square root of 2, x plus the square root of 2 rather, times x minus the square root of 3, and x plus the square root of 3. Now, to remove the preconceived bias that you will have as to what these numbers mean, you will be visualizing them as some point on the real line. We're going to rename these roots. I'm going to rename square root of 2 as x. I'm going to rename square root of 3 as y. So x squared is equal to 2 and y squared is equal to 3. Okay, so my field extension in which this splits is going to have the form k is equal to, and the ground field, by the way, was the rational numbers. So our ground field is the rational numbers. Our splitting field is going to be of the form q0 plus q1 times x plus q2 times y plus we're going to have q3 x times y. Now if you multiply again, so what could we do further? We could multiply x by x times y and we could get x squared y, but then we'd replace x squared with 2 and we'd go back down to something here. So everything that you could possibly get is there. That's a field. So you can add any two elements in here, you can multiply any two elements in here, you'll come back to an element in here. It's the smallest field that contains both x and y. It also contains the other roots because minus x is going to be in here and minus y is going to be in here. And that is our splitting field here, basically. So you could try and find the field automorphisms of this splitting field. So let's suppose phi is an element of Galois of k over q in this case. So it's an element of the Galois group. Then we're going to act phi on some element of our splitting field, q3xy. So our general element of the splitting field looks like this. Now, because we want phi to be a field automorphism, we are supposing it is a field automorphism, therefore it obeys the field automorphism properties. And indeed, we can split up the addition like this. So we can split it up into phi of q0 plus phi of q1 times x, but because it's a field automorphism, we can split that into phi of q1 times phi of x plus phi of q2 times phi of y plus phi of q3 times phi of x times y, but again, because we want it to be a field automorphism, that should be phi of x times phi of y. Okay, so we are defining our field automorphism to be that. All we're doing basically is we've said we're following our noses effectively. If it's going to be a field automorphism, it has to obey that. We have no choice in the matter. Now, it's an element of Galois group. It's not just any old field automorphism, it fixes this ground field. So all of these have to be fixed because they're all rational numbers. So q0 plus q1, and I should have, yes, that's fine. Phi of x plus q2 phi of y plus q3 phi of x phi of y. So that is basically all you need to tell me, basically, is where the roots go. And I already know that if it's going to be in here, it has to map roots onto roots. So we know that these mappings, basically, this mapping now is completely determined by a field, by a permutation of the roots. I know that if phi is an element of the Galois group, of Galois of k over q, phi must map roots onto roots. Must map. Oh, that lamp is really annoying. Roots onto roots. So each field automorphism automorphism is reduced down basically to down to a permutation of the roots, down to a permutation of the roots. So in this case we have 4 roots. We have the square root of 2, we have x, minus x, y, and minus y. So it's going to be a subgroup of S4, which is the number of all the possible permutations of these. So let's investigate further the condition for it to be a field automorphism. So all we've done so far is we've followed our nose. We've said if it's a field automorphism, then phi has to map it onto this. So in fact, all you need to tell me is where x, y, and x and y, where x and y go, and then I know everything basically. And we know that those have to go onto roots. That simplifies it further, in fact, from being a subset of S4, because the only freedom you have is telling me where x and y go. As soon as I know where x goes, I know where minus x goes as well. So you don't have as much freedom as S4 suggests. Does it go down to D4? I think it does go down to D4, because if you think about it, it's the symmetries of the square. Because if you think, we could put x and minus x there, we could put y and minus y there, and as soon as you tell me where x goes, I know where minus x goes, because it has to go to the opposite one, if you like. So if I send x to negative x will go to x. If I send x to y, negative x will go to negative y. That seems about right. So it reduces down to D4, basically, just because all I need to know is where x and y go, and the other two are determined by that. Okay, so we've gone down from S4 to D4, the symmetries of the square. Where are we going further? Oh, we want to look, because I haven't shown you that this is actually a field automorphism. So we need to check that if I take phi of q0 plus q1 x plus q2 y plus q3 xy, and I add on q0 bar plus q1 bar q1 bar x plus q2 bar y, and then plus q3 bar xy, I need to show you that that is equal to phi of this one plus phi of this one. So what I can do is I can add these two together, so I get phi of q0 plus q0 bar plus q1 plus q1 bar, so I'm just using the distributive property of the field, q2 plus q2 bar times y plus q3 plus q3 bar times x times y. Okay, that's good. So now I know what this has to be sent onto. It's sent onto q0 plus q0 bar plus q1 plus q1 bar times phi of x plus q2 plus q2 bar times phi of y plus q3 plus q3 bar times phi of x, phi of y. Okay, so now I just apply the distributive property again and multiply these all out. q0 plus q1 phi of x. I'm just splitting it up, multiply everything out and rearrange by commutativity. Plus q2 phi of y plus q3 phi of x, phi of y, and then I get plus q0 bar plus q1 bar phi of x plus q2 bar phi of y plus q3 bar phi of x, phi of y. And then, just to labour the point even more, I will rewrite this as phi of q0 plus q1x plus q2y plus q3 x times y plus phi of q0 bar plus q1 bar x plus q2 bar y plus q3 bar xy. So therefore it does automatically satisfy the properties of being an additive, the additive properties of being a field automorphism. So just because I followed my nose down here when I was defining this, it automatically has obeyed the properties that I needed with regards to addition. So I don't get any additional constraints on my permutations from that property. So let's go to the other one, multiplication. Multiplication does give me another constraint. So if we look at phi of q0 plus, let's move this up, phi of q0 plus q1x plus q2y plus q3xy times q0 bar plus q1 bar x plus q2 bar y plus q3 bar xy. So if I look at that, now please do not make me write out all 16 terms of this expansion. We want to prove, obviously, that this is equal to the claim, well, not the claim, we want it to be equal to, maybe I should just write it all out. Okay, I'm going to write it all out just to make, because it's probably just simpler just to do it than try and explain what's going to happen. So if we multiply it out, q0 bar plus q0 q1 bar x plus q0 q2 bar y plus q0 q3 bar xy plus, now we'll multiply this term here. Oh, I should have collected like terms actually. Start again. We'll go a bit more complicated rather than doing it like that. We will collect terms. So what term is going to be a constant here? No, this is getting too complicated already. No, I do know how to do this. Right, okay. So what I'm doing is basically I'm going to collect up the constant terms first and all the terms. So I'm going to collect all the terms with an x and all the terms with y as we go along. So constant term, we're going to have q0 bar. What other terms are going to give us constant? So have a little think. This times this, we're going to get x squared, which is equal to 2. So that's going to give us a constant, plus 2q1 bar, okay, plus, oh no, yeah, I can't do this, otherwise it'll be more difficult to see what I want you to see if we do it that way. Okay, so no, we're going to go back to the original, which I've crossed out, so do it again, q0 times q0 bar plus q0 q1 bar x plus q0 q2 bar y plus q0 q3 bar xy plus q1x, oh no, q1 q0 bar x plus q1 bar x squared plus q1 q2 xy, q2 bar that should be, plus q1 q3 bar x squared y plus q2 q0 bar y plus q2 q1 bar yx plus q2 bar y squared plus q2 q3 bar xy squared plus q3 q0 xy plus q0 bar, that should have been, plus q3 q1 bar x squared y, and I'm starting to lose the will to live. Okay, plus q3 q2 bar xy squared plus q3 bar x squared y squared. There we go, we've done. So if we want to multiply, if we want to decide what that is, what we have to do now is do what we've done all along. So it's a field automorphism, so we can split it up term by term, adding it. We can then split up the multiplication because it's a field automorphism, and because it's an element of the Galois group, we can fix all the rationals. So this will become q0 bar plus q0 q1 bar times phi of x plus q0 q2 bar phi of y plus q0 q0, q3 bar phi of x, phi of y, plus, where are we now? q1, q0 bar phi of x. Okay, keep going, must keep going. Okay, so just keep swimming. Plus q1 bar phi of x squared, plus q1, q2 bar phi of x, phi of y. So it's just brute force here. Plus q1, q3 bar phi of x squared, phi of y, which I haven't got room to put. Right, we need another piece of paper, but I don't want to turn over off that. So, okay, so where are we now? Where did we get to? We got to q1, q3. I think we must have been there. Okay, so plus q2, q0 bar phi of y, plus q2, q1 bar phi of y. Oh, phi of y, phi of x. Wait, sorry, I have made a mistake here that I wish I hadn't made. I've defeated the whole point of this silly exercise. The point of this exercise, and just by going into mindless calculation mode, I have defeated the whole point of this exercise. You see, what I've done here is I have replaced things like phi of, I've replaced things like x squared with phi of x squared. It should be phi of x squared. I do not know that phi of x squared is equal to phi of x, phi of x. I never defined that. In my original definition, did I define that anywhere? No, I did not. I did not define that that was going to be the case. So, if it's going to be a field automorphism, the condition is that things like this are going to have to be true. And equivalently here, no, that one's fine. I defined phi of x, y to be phi of x times phi of y. But here, I took phi of x squared y, and I just said it was equal to that. I did not know that. That was a condition. And indeed, if it's going to be a field automorphism, that has to be true. But that is the condition for it to be a field automorphism, not something that was true by my definition. So, in fact, what you're going to see, and I'm going to say that we've done enough of this calculation now because I'm getting tired. If you want to see what I was trying to show you, what you can do is you can multiply all of this out, like I have done, put phi of this in, but write all of these things like this, where you don't know that phi of x squared y is what you want it to be equal. Just write phi of x squared y. Then what I advise you to do is turn each of these great big things here. I advise you to write out what they are. So q0 plus q1 phi of x plus q2 phi of y plus q3 phi of x phi of y, and then the other one, which is q0 bar plus q1 bar phi of x plus q2 bar phi of y plus q3 bar phi of x y phi of y. And basically, if this was going to be a field automorphism, then phi of these two things multiplied together would have to equal phi of this one times phi of this one. This is phi of this one, this is phi of this one. So, multiply them together, and this would have to equal this thing that we've got up here, which is what we got when we multiplied them together first, and then translated them. And basically what you'll find is that for this great big long multiplication to be the same as this great big long multiplication, what has to happen is that things like phi of x squared needs to equal phi of x times phi of x. It will work if that is the case. In fact, phi of any algebraic structure you can come up with, which is made out of the roots, So take the roots, add them, multiply them, do field operations to them, and get me something, and basically phi of whatever you come up with, so whatever you come up with, so for instance x squared y z cubed plus x y x must obey field automorphisms, but it must obey the properties of the field automorphisms. So you must be able to split this up into phi of x, phi of y, phi of z cubed plus phi of y, phi of x. So basically, if it's going to be a field automorphism, the point is that it will be a field automorphism if it fixes, if it's true that phi of x, that phi of any of these algebraic structures is it's split up like a field automorphism. If that's the case, then it is true that it will be a field automorphism, and that you can define a field automorphism as we did by this, by phi of this is equal to this thing here, where this is the permutation of the roots, such that all those things are satisfied. And that implies that since this was going to work, that what has to happen is if you take any algebraic structure like this and you know it's equal to some rational, it must fix that equation. So for instance, if I take phi of x squared, we know that phi of x squared was equal to 2. We know that phi of 2 is equal to 2. Therefore, what we have to find is that phi of x times phi of x is going to be equal to 2. That tells us something about the permutations. If I put in y here, and I multiply it by y, so if I let phi of x equal y, is y squared equal to 2? No, y squared is equal to 3. If I let this equal negative y, no, again, it equals 3. So you get contradiction. But if I let it equal negative x, then negative x times negative x is equal to 2. So now let's use this to calculate the Galois group for the biquadratic extension. Galois group for biquadratic extension. Okay, so we had this equation x squared minus 2, x squared minus 3. And in fact, basically, what we could generalize this to any polynomial ax plus b, x squared plus cx plus d. And basically, what you can find, you can always find equations that the roots satisfy in this case. So we'll continue with the easy example that I've got up here. So in this case, I can find the obvious examples of equations that this satisfies is that x squared is equal to 2, or y squared is equal to 3. These are equations that the roots satisfy. So when I look up for permutations of the roots that are going to fix these, if we permute x and negative x, so if we take this for instance, well, we could leave those alone initially, so we could leave these two alone. We could map this one onto y, this one onto negative y, so we could leave those alone. This is a permutation of the roots here. So this fixes this equation, and it fixes this equation as well. So that is hopeful as a permutation that could be plausible. So in fact it is an element of this Galois group. So you can come up with other equations that these satisfy. None specifically leap to mind. I don't know if you can actually. What other? I think in the case of a quadratic, those are probably the only equations that you can come up with. In a cubic, certainly you can come up with more equations, and that this thing will have to satisfy. Okay, so that has to be 1. So other permutations we could look at. We could look at the identity. So that's definitely in there. Y, negative y, negative y. And we know we could try mapping y onto one of these two, but it won't work, because as soon as you do that, this equation will break. So we have to map y onto negative y or y. So in fact we could map it between those, so we could leave those two fixed and we could interchange y and negative y, and that will leave both of those equations fixed. So there's a permutation. Or we could swap both of them at the same time, and that will leave both equations fixed as well. So those are the Galois, are the permutations in the Galois group, and those permutations, if you use them to create, in this way, to create field automorphisms, you can find the field automorphisms of this. So maybe we should do that. So for instance, so field automorphisms, you can correspond exactly to this, basically. I don't know if I want to do it. You can send this to negative x here, so that will put a negative in front of here, and it will also put a negative in front of this, because it will send this to negative x. If you do this one, it will leave it exactly alone. If you do this one, it will put a negative in front of there, and a negative in front of there. And if you do both of these, then it will put a negative in front of there, a negative in front of there, but because you've done both of them, you'll get two negatives, so you'll get a positive in front of there. And those are the field automorphisms, effectively. And as I said in the initial video, they are analogous, in a way, to complex conjugation. So the Galois group in this case, you might recognise this group. It's the Z2 cross Z2, which is the climb 4 group, sometimes given the symbol V4. And there we go. That is the Galois group for a biquadratic extension. We will use this concept of looking for permutations of the roots, such that every algebraic equation you can think of, which consists of the roots and elements of the ground field, is still true after you permute the roots in that way. We will use that in the next video to find the Galois group of a cubic equation.